Everyone, I'm Ke-Xin from Team TruSense. Our device vision is easy to handle. There is a yellow cartridge here, so chips in, results out, it is processed automatically. Here is our test process. It only takes 4 steps and 5 minutes to give results. After collecting blood samples, you push the chips into the cartridge, and then you can take a sip of coffee to wait for the results. Our results benefit from our chips and data processors. First, I'd like to introduce our chips. We choose adjustable base for our chips, which is porosilicons. Proper size of porosilicons related to detect molecule size is aged by controlling current densities, and then a polylysine amplification layer was introduced to link this adapter to porosilicons. Then we assembled our chips as a sandwich, consists of fluid channels, silicon wafer, and copper backing. This to make it stable for transportations and make it possible to process automatically. This lifting injection platform is equipped with sensors to make sure our chips was placed in the right directions. So the users won't need to be well trained for use our device. Next, I'd like to introduce our data processors. Our detection principles is based on this interference reflection spectrum, and the spectrum data will be processed by linear fitting algorithms to give effective optical thickness, which is to determine the amount of adamant bindings with our adapters on porosilicons. But for the users, after converting, you can just click the buttons to sort your results, and you can also trace back to your previous results, so it's readable for users. We have excellent supporting service because our silicon wafer is can be recycled, so low burden, low environmental burden, and our device was assembled modularly, so low replacement cost. Last but not least, I want to emphasize our custom-built algorithms. Linear fitting algorithm is what we use today because it's suitable for single-layer porosilicons, and FFT is used for multiple-layer silicons, which can be a big pore silicons on top and a smaller pore below. So when sample flow throughs, it can serve as a filters. So we are ready for smaller molecules. And IAW have higher sensitive, but it requires more stable environments, like an air table, since atomic map is big in size and we don't have air table today, so we choose linear fitting. I'd like to thank all the institutes and companies for funding and support us. We just got an acceptance letter from 2019 International Conference on Biotechnology and Medical Engineering in Beijing. Thank you so much. Thank everyone and my team members to make it happen. Thank you.
Yes. Thank you for a very nice presentation. And it's a very interesting technology that you have chosen to use. So you fabricate the silicon nanostructures yourself? Do you fabricate the silicon nanostructures yourself?
Yes.
Is it custom made? And you build the whole system yourself?
Yes,
right?
we each in laboratory use HF.
Yeah,
Yes.
you did it yourself. Now, in your test results, you didn't really give us any limit of detections, or have you achieved any results on the actually measurements yet?
During our test, our limit of detection is 0.5 microgram per milliliter, and we do the calibration curve during 0.5 to 10, but we also test if 25 microgram per milliliter has a response.
Okay. And the time of your measurements, can you do it in the 5 minutes span?
Yes, because we have already test the baseline of the chips and chemical modification it. So when testing, the actually step we are going to do is washing the chips.
Right.
So 5 minutes is we test is good for our results.
Okay, I just have to clear. And so can you tell me a little about your calibration assay? Because this is very important for interpreting of your results, right? Because it kind of varies a little. So did you, your calibration algorithm?
Oh, we use these linear fittings, and we have this photo here. Oops, this one.
Yes.
Because we use these interference reflection spectrums,
Yeah.
and what causes changes is the index of refractions.
Yeah.
So the equations we have is effective optical thickness equal two multiple index of reflections and the length of the light. So what we do here is to move the the index of reflection which changes to the left side and make a
but you don't need to go into that much details. But I'm just interested. You write these algorithms to actually model this yourself.
Yes.
Yes.
We actually write 3 kinds of algorithms.
Yeah,
right? Yes.
and you chose the linear because you saw the other one was not as precise. So I think it's excellent work, and I think you really analyze the data very truly. Now, do you need any pre-preparation for your sample?
No, for samples, just for chips.
Yeah, but you do, as far as I understand, you do need to surface modify the chips before you actually do the measurements, right?
Yes.
Yeah. So that takes some time, right?
Yes.
Yes. So you do, yeah. Okay. But thank you very much.
Thank you.
Yeah, thank you very much for the presentation. There's one thing
you.
I would like a clarification. So you had an adapter linker. What is the adapter linker? So
it's TNF alpha.
no, okay. So the adapter, the word adapter is TNF alpha.
We draw this for admin map.
Okay, but I'm okay. But then you. So what's? I'm not sure if I understand. So you have TNF alpha that is bound to the chip, but then you seem to have a chemical bond to the antibody. So this is what I don't understand. I'm sorry.
Sorry, he's for the chemical.
Let me see the proofs. Sorry. Yes. First, the silicon is kind of waterproof, so we have to make it easy to connect to the water. This is the first step, and we oxidize the silicon wafer. This is the first step, and in order to increase the signal, we have to connect the anhydride group to the silicon wafer, and with an amino group on the other side, they will combine. And we use the poly-L-lysine or chitosan to increase the group, and that will increase the signal. And at the end, it will be the TNF alpha and some left anhydride group. And we use an end capper to close all this anhydride group.
Okay, so you bind the TNF alpha on the polylysine, and
yes.
then
and it's through a covalent bond, so it's pretty strong.
No, it's clear now. Thanks.
Yes, thank you.
Thank you very much. Very interesting concept, interesting presentation. I was wondering, you use at the moment plasma, right?
Yes.
Or not? Have you tested whole blood? Because the technique seems, well, perhaps possible to also do an analysis on whole blood.
We actually didn't try whole blood, but when we interwesting this method, we see that some people use it to detect the bacteria in the whole blood, because these pores can be afflicted if in whole blood the challenge is the blood cells. They are much more bigger than proteins, so they will not enter the pores and they will be washed away.
All right.
Yes.
Yeah. Okay. Okay.
Thank you.
Interesting.